Hi, my name is Ada Taylor, and today I'll be sharing our work on diminished reality for close quarters robotic telemanipulation. Our motivation for this project was to address the issue of occlusion during close quarters manipulation tasks. When a human is teleoperating a robot arm, in scenarios ranging from assistive robotics within the home to larger scale manipulations in a factory setting, the user's view of the objects they aim to interact with can frequently be occluded by the arm itself. While changing perspective can address this issue, that requires extra energy and inconvenience and may not always be tenable for users. In prior work, a variety of strategies have been deployed to address the problem of occlusion in telemanipulation, including with the use of augmented reality. These approaches range from projecting alternate views of the scene recorded by onboard cameras in augmented reality for the user, as seen to the left, to mounting cameras within the hand of the arm itself, to having an entire secondary arm apparatus to maintain an unoccluded camera view of the workspace, as seen to the right. To address this problem, we introduce a new visual interface for teleoperation based on a variant of augmented reality called Diminished Reality. In Diminished Reality, real-world objects are visually erased from a scene when viewed through a head-mounted display like the Microsoft HoloLens. In our case, the robot arm is erased so the operator can see the occluded objects behind it. We achieve this by localizing objects in the scene relative to the robot arm using a network of cameras, then overwriting pixels in the HoloLens display over the parts of the arm that occlude the objects from the user's perspective. This creates the illusion of invisibility seen here. We specifically introduce two diminished reality visualizations. In the first of these, invisible, the robot is completely erased from view. In the second visualization, the arm remains invisible with the addition of a translucent outline of the arm to help users keep track of its position, a feature requested by pilot users. For both of these, our solution differs from existing solutions by naturally extending the user's previously existing viewpoint. They don't have to juggle a secondary viewpoint in their head. To investigate the potential benefits and drawbacks of these visualizations, we conducted a 36-person user study in which users operated a robot arm to complete a simple manipulation task. We compared user performance in two cases: an occluded case, where the target object would be occluded by the robot arm during a manipulation, and an unoccluded case, which acted as a control. Specifically, we asked users to use a Miko robot arm to pick up a Pringles can and move it to a target location. Users completed the task 3 times in each of the occluded and unoccluded cases, once with the invisible visualization, once with the outline visualization, and once with no visualization, which acted as a control. As we can see in this diagram, from the left seat, the user has a clear view of the Pringles can, and the arm approaches from the side. However, in the right seat, the user has to look directly through the robot arm to find the Pringles can. To characterize the impact of our diminished reality interfaces, we investigated 4 hypotheses on the topics of effort, efficiency, user preference, and relative performance across occlusion conditions. Overall, we hope the ability to see through the robot in the case of occlusions would decrease effort, improve efficiency, be preferred by users, and raise performance to match the unoccluded case. We believed if the target was occluded, users would move their heads less and report lower difficulty when the robot is either invisible or outlined. We thought that the ability to look through the robot would help users, and that users would prefer modes that gave them the most information. We also thought that addressing occlusion via the invisible and outlined modes would raise performance to match that of the unoccluded condition. In order to test these hypotheses, we conducted a user study with 36 participants recruited from the local community. Users were given between 5 and 45 minutes to complete a tutorial introducing them to how to operate the robot arm. They then completed the task with each of our 2x3 combinations of occlusion conditions and diminished reality visualizations. To account for ordering effects, particularly due to users becoming more proficient with operating the robot, we presented these modes in randomized Latin squares orderings. We collected data and direct feedback after each trial, and overall feedback at the end of the study. During each iteration of the teleoperation task, we specifically measured features such as the movements of users' heads and the time required to complete the task. We also used the NASA Task Load Index to survey users about their subjective workload in each of the modes, allowing us to break down user perception of task difficulty in 7 different categories of mental and physical effort. After the entire set of trials was complete, we asked users about their preferences among the modes in both the occluded and unoccluded cases, and asked them to describe the most difficult aspect of using each mode. In the interest of time, we've chosen to summarize some of the most interesting results here. The most notable result is that the diminished reality visualizations do indeed seem to decrease physical effort required. Here, we can see a heat map representing the overall movements of users' heads across all subjects in the occluded case. The larger red area, in the normal mode to the left, as compared to both the diminished reality modes to the right, illustrates a qualitative difference in the amount of head movement, though this was not statistically significant. However, with both diminished reality illusions, we found that there's a lower average head deviation from the start position. Specifically, as we can see to the right, in the occluded case, the average deviation of the head location from a neutral ergonomic pose during the trial was higher for the normal mode without the aid of a diminished reality illusion. Users' heads are farther off-center on average. Note also that all modes perform about the same in the unoccluded case, when head movements aren't necessary, and as expected, their positions are even closer to neutral. Intuitively, this indicates that users tended to hold their heads closer to an ergonomic, neutral position without tilting their heads when using diminished reality. Without the advantages of being able to see through the robot, users held their heads at a larger deviation from center to get an unoccluded view and complete the task. We had expected to see more overall movement over the course of the trial, but instead users tended to find one pose and stay with it for long periods of time. And of course, this still has a physical impact on the user, as anyone who sat at an awkward angle at a computer while distracted by a task can attest. At the same time, users reported that using the diminished reality illusions was more temporally demanding and frustrating than in the normal case, indicating that these modes added a drawback in terms of mental effort. Here we can see the different categories of the NASA TLX. We found significant differences in the categories of temporal demand and frustration, with significant differences between the pairs of normal and invisible, and normal and outlined in temporal demand, and approaching significance with the same pairs in the category of reported frustration. So while our diminished reality interface did provide an improved understanding of the occluded space, and therefore helped users avoid having to change viewpoints to complete the task, these new visualizations added complexity for the user. Despite the positives in terms of physical effort, users found drawbacks in these categories of mental effort. We found another design trade-off in our study. We also found that when the invisible interface was used in the unoccluded case, when it was not needed, it was reported to be the most difficult mode to use. Here we can see the different modes ranked by difficulty in the unoccluded condition. The normal mode, to the left, with no novel visualization, is consistently ranked the least difficult, while the invisible mode, in the middle, is most often ranked the most difficult mode in this condition. Because this increase in difficulty was not reflected in our physical measures of the task, this may reflect a larger cognitive load for the user, perhaps due to the additional complexity of keeping track of the location of an invisible arm when it does not provide added value. Users seemed to feel like they lacked their usual proprioception of the arm, saying it was disorienting that they couldn't see the robot arm at all, although they could see the Pringles can, or it was hard to understand where the arm was, and that they were getting the background confused with what they were seeing through the lenses. They didn't know where to look. On the other hand, we also found that providing too much information with our visualization might also have drawbacks. In the case where the arm had an outline, in addition to occlusion, users took longer to finish the task. This likely corresponds to comments by users indicating that the outline added more visual clutter, and watching out for both the arm and the object and the overlap was confusing. This makes sense, as in this case users were attempting to see through the outlines of several layers of robot joints in order to see the object. From these findings, we believe that diminished reality does hold potential for addressing occlusion in teleoperation scenarios. Giving users the ability to manually or automatically turn illusions on and off could address the issues of unnecessary indivisibility or visual clutter that we indicated, though the system itself could also increase mental overhead. This could allow users to better align the information provided or removed by the diminished reality view to match the current task requirements. Finally, it would be valuable to conduct this study with users who have upper body motor impairments or who use this robot on a daily basis. We'd like to thank our sponsors who made this research possible. This work was supported by the JSPS Program for Fostering Globally Talented Researchers, the NACE Bilateral Research Grant, the National Science Foundation, the Paralyzed Veterans of America Research Foundation, and the Sony Corporation. In summary, we found that diminished reality and close quarters teleoperation can mitigate object occlusions by the robot and may lead to less physical effort for the user at the expense of increased mental effort. Thank you for your time. If you have any questions, you're welcome to ask them now, or you can write me at ADAT plus IROS@cmu.edu. Thank you again for your time.